No.
Okay, we are recording third period geometry on Wednesday, May 11th, and we're doing a little bit of review for the end of course exam. So we're doing some questions, talking about them, and taking some notes. So the first question was to write a converse of a conditional statement and then determine whether the converse is true or false. If it is false, you have to find a counterexample. And yeah, that's all one word, counterexample. So here is your conditional statement. And first, what's a conditional statement? How do you know it's a conditional statement?
It has a hypothesis and conclusion.
Yeah, hypothesis and conclusion,
I have an idea.
Yeah.
I'm gonna write this down. So,
Okay.
Yeah, so
if you
remember, I'm just writing down that.
Okay.
How a conditional statement has what?
A hypothesis and a conclusion.
Yeah, I'll just put the remember in there so you know
Okay.
that it is. Okay.
Good.
So,
All right.
statement.
So here's the statement. If you have a dog, then you are a pet owner. If you have a dog, then you are a pet owner.
Some people might think, what does this have to do with
No,
geometry?
what are we doing again?
If you have a dog, then you are a pet owner. So this is a conditional statement, right? If then, what's the hypothesis?
If you have a dog.
If you have a dog.
If you are a dog, oh, no, I didn't.
And what's the conclusion?
Then you're
a pet owner. Okay, now you need to write the converse to this statement. So what does that mean we need to do?
You flip the statement.
You flip the statement. All right.
Like if you are a pet owner, then you have a dog.
All right.
That might not be true.
If you are a pet owner, then you have a dog. Don't say might. You just use the same words. Then you have a dog. Okay, that's the converse, right? Because you flipped it, as you said, right? You flip it. You flip the conclusion to be the hypothesis to be the conclusion. So now, is that true or false? If you are a pet owner, then you have a dog.
I would say that's false.
It's false, and so you have to provide a counterexample. Why is it false?
Because not everyone has a dog.
Exactly.
Yeah. You could have a cat, you could have a bird, you could have a fish, you could have a horse,
Chicken.
you could have a chicken. Okay, right. So there's your counterexamples, right? You could definitely provide more than one counterexample. Now, you just did this as a short answer style of a question. If it was multiple choice, here are some choices for you to choose from, and you would have to find the best one. If you are a pet owner, then you have a dog. True. Well, they wrote it correctly, didn't they? But it's not true. A dog owner owns a pet. Okay. That's true, but it's not the converse, is it? If you are a pet owner, then you have a dog. False. You could have a hamster. Oh, that one sounds like that's going to work, doesn't it?
Yep.
The last choice is, if you have a dog, then you are a pet owner. Well, they just rewrote it again, and that's false. You could have a hamster. So the third choice was the best choice, wasn't it? Okay. So if you had to make a choice, you'd go through and carefully read your choices and decide which one works for the solution you came up with. All right? Any questions on those? On that one?
No.
Okay. Let's practice something else, though, with the same statement, just for fun. So we did the converse with the same conditional statement. If you have a dog, then you are a pet owner. Okay.
What?
Let's write the inverse.
What did you do?
I did. Oh, I gotta delete those few words.
Let's
Check
write
this out.
Let's write the inverse. Let's keep
All right.
focused on this. Let's write the inverse to if you have a dog, then you are a pet owner. What's the inverse mean?
The opposite?
No, converse is, Well, okay, sorry, Tabitha. What do you mean by opposite?
Like it's if you want if you don't have a dog.
Yes, good. You're right. The opposites. You negate everything, right? So if you don't have a dog, then you are not a pet owner, right? If you don't have a dog,
I didn't do it.
then you are not a pet owner. That's good. That's an inverse, right? So converse, we flip it. Inverse, we negate it or opposite. Contrapositive, we do both things, don't we?
Yeah.
We flip it and then negate it. So we would say,
Right.
if you are not a pet owner, then you do not have a dog.
Yeah.
Well, that would work, wouldn't it?
Yeah.
Yeah. Okay. All right, so you remember all those?
Yeah.
Great.
I'm going to tell you the mistake I made.
What? You made a mistake?
This is funny. I wrote the statement. I'm going to delete what I wrote as a mistake, but by accident I wrote, if you have a dog, then you are a dog, and then you have a pet owner. Or
Oops.
You are a pet owner.
All right.
I'm going to fix that. It's okay. I can fix that. That was funny.
What kind of reasoning do we use when we look at patterns and make statements about them? You remember that? Are we using inductive, deductive?
I don't know. I'm between the two.
Yeah.
But
Well, remember way back when
I'm not doing working with patterns.
we were working with patterns, right? And when you're making a conclusion based upon a pattern or example, you're using inductive reasoning, okay? When you make a conclusion based on a pattern of examples or past events, you are using inductive reasoning. And in geometry, that's what we do. Inductive.
It's hang on.
Inductive.
So when a conclusion is based on a pattern, that's inductive reasoning.
Yeah, and that's what we do in geometry, isn't it? We make these statements based upon noticing these patterns of things. So like a test on this particular practice exam says, which term best defines the reasoning used below? Abdul broke out in hives the last 4 times that he ate chocolate candy.
That's sad.
Abdul concludes that he will break out in hives if he eats chocolate candy. He's made a statement, hasn't he?
Mm-hmm.
Has he used inductive reasoning, deductive reasoning, converse reasoning, or inverse reasoning? Now, what 2 choices could we throw out?
Inductive or inductive?
Well, inductive, deductive we want to use, right? We want to think about those. Those sound similar. Is there anything as converse reasoning and inverse reasoning? No, those are just something we're doing to the statement, right? So we have to decide between inductive and deductive. Inductive is noticing a pattern and making a statement. He noticed a pattern. And each time I'm eating chocolate, I break out in hives.
Yeah.
I'm going to make a statement about that. All right? Okay, let's write this statement down and do some work to it. If a triangle has 2 congruent angles, then it is an isosceles triangle. Isosceles. ISOSCELES.
Oh, that one.
If a triangle has 2 congruent angles, then it is an isosceles triangle. All right. And we're given this statement that's a valid geometric statement. You recall the definition of isosceles triangles. They're going to have two equal sides, therefore two equal base angles, right? So we're like, oh yeah, if a triangle has two congruent angles, then it is an isosceles. All right. We need to write the contrapositive to this statement. So what do we need to do for a contrapositive?
Do flip it and negate it.
Flip it and negate it. Good. All right. So how would we flip it? We'd say
So
if a triangle is not
if
isosceles?
Is not isosceles,
Mm-hmm.
then it does not have two congruent.
Then it does not have two congruent angles. Nicely done.
Yeah.
That is the contrapositive, isn't it? If a triangle is not isosceles, then it does not have two congruent angles.
No.
Is the contrapositive statement valid? Explain your reasoning. If a triangle is not isosceles, then it does not have two congruent angles. Is that a true or false? If a triangle is not isosceles, then it does not have two congruent angles. What else would it be? What other kind of triangle would it be if it's not isosceles? What kind of triangles do we have? What are our classifications of triangles?
Well, we also have equilaterals.
Equilateral. Let's see if equilateral would work for this. So an equilateral has what for its angles?
They're congruent.
They're all congruent, aren't they?
Yeah.
So if a triangle is not isosceles, then it does not have two congruent angles. No. An equilateral triangle has two congruent angles, doesn't it?
Exactly. So an equilateral could still be considered an
isosceles, yeah. So that's how you probably explain it. Well, an equilateral has three congruent angles, and it's an equilateral, but it's also isosceles.
Because it meets the criteria.
Yeah, so that's a little tricky one, isn't it? This one's tricky. You'd have to explain it and say,
You have to give your argument.
Mm-hmm, exactly. All right?
It's kind of
Makes you think, doesn't it? Yes. All right, here's another statement. Let's do some work with this one. Ready? If a quadrilateral is a kite. Yeah, so kite shape, right?
Yeah.
Then its diagonals are perpendicular.
I haven't seen a kite for so long, so I don't know.
Oh, I know. We have to think about this. What would a kite look like? Well, the choices are if a quadrilateral has diagonal, or they want you to see which of the following is the inverse statement to this. So if a quadrilateral is a kite, then its diagonals are perpendicular, and this is a valid geometric proposition. Okay, a kite is a quadrilateral. Typically, the two sides that come together at the top vertex are equivalent, and the two sides that come together at the bottom vertex are equivalent, and they join together, and the diagonals are perpendicular because it makes a cross-like member, a T-like member in order for the kite to fly. All right? So that is a valid statement. So let's do the inverse of that statement. If a quadrilateral is a kite, then its diagonals are perpendicular. What would the inverse look like?
If the quadrilateral isn't shaped. What? I'm doing wrong.
If a quadrilateral is not a kite?
Is not a kite.
Okay.
If it's not a kite, then its diagonals are not
not a kite, then its diagonals are not perpendicular. All right, that's a good one. Okay, let's see what choices they give. If a quadrilateral has diagonals that are perpendicular, then it is a kite. Is that an inverse?
Oh, really?
That sounds like almost a converse, huh? If a quadrilateral is not a kite, okay, we said that, then its diagonals are not perpendicular. Ding, 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 ding.
Yeah,
That's our
exactly.
choice, isn't it? Because the next one is if a quadrilateral has diagonals that are not perpendicular, then it is not a kite. That's a converse, isn't it? Or that's a contrapositive, excuse me. If a quadrilateral is a kite, then its diagonals are not perpendicular. All they did was negate the last statement. You got to negate both, right?
Yeah.
So that letter B, that second choice, was our choice.
That was
They didn't
good.
ask us to prove it. They didn't ask us to give a counterexample. They just wanted you to do it, pick out the inverse. Okay? All right.
Sounds like some of the stuff we were doing yesterday. You were
Yeah, I know. This kind of is a
Conditional
good review. Conditional statements. That was a nice review there of those
way back in
conditional
chapter
statements.
1 or 2 or something
Yeah,
like that.
chapter 1. Can you believe it? Chapter 1.
Where did the time go?
Where did the time go?
No, I can't
Oh, I
believe it.
know. Right. Where did the time go? From September. All right, let's see. What else do we have? Any more practice questions for those? Let's see. Looking here. Conditional. That's a lot of practice for conditional statements. We did a couple yesterday. All right, let's do something a smidge different. Let's answer some other questions that are kind of basic geometric statements. Which of the following kinds of statements cannot be used as a reason in a proof?
Can you read the questions I can read out?
Which of the following kinds of statements cannot
Whoa.
be used?
Well, hang on. Whoa. Okay, which of these? I'm sorry, my brain went to something funny.
Which of the following statements
Cannot be used as a reason in a proof. In other words, you cannot use them in court, right? In geometry, court, cannot. So your choices are A, theorems, B, defined terms,
Define or defined?
defined terms, C, postulates, D, assumptions.
I would definitely go
That
with
was
D.
kind of an aha, like, really?
I
would definitely go with D.
Good.
Okay.
Good. You
She
can't
had to check.
assume. You can't
just assume that something is
get right. Good job.
I would
Yay.
absolutely
Be like,
go with
I think so.
I think so, or just look at it. It looks like it, right? Okay, good.
But
That was a
actually,
fun one, wasn't it?
yeah.
It was.
All right. Complete the following statements.
Sorry.
Mhm.
Writing this is the work practice quick.
All right.
Good idea.
I'm loading.
You can't do that from watching
Yeah, I do. Okay.
because you don't have fingerprints.
All right.
Oh, I do.
Ready to complete the following statements? Okay. The ceiling and the floor of your kitchen are examples of blank planes.
So, the ceiling.
And the floor are examples of blank planes. So you got a plane on the floor running into infinity, and you got a plane on the ceiling running into infinity. What are they examples of to each other?
Parallel.
Parallel. Good, Justin. Yeah, they're never going to touch, are they? Parallel planes. Now, the floor and the wall to each other What are they examples of? Examples of blank planes.
I guess they're perpendicular.
Perpendicular, nice. They intersect and they're perpendicular. Right angle. Dang. You could say intersecting planes if you wanted to, but you could also say an example of perpendicular planes because they're coming down at a right angle. As long as the house is square, I guess if it's a leaning house, the wall leans, you could say they're just intersecting. You don't know yet.
Mm-hmm.
Good, excellent. Yeah, right. Okay, complete the following statement. 2 lines that do not lie in the same plane are called blank lines. You have some choices. So 2 lines, they do not lie in the same plane. So you might have a line going through your ceiling at a certain slope, and then you have a line going through your floor at a certain slope, and it's just running through its floor into infinity. And you know your ceiling and your floor are parallel to each other, right? But these lines up there are going in different directions. They're not parallel to each other, but they don't intersect either. Okay? Do they? Because they're in parallel planes. So would we call them coplanar lines, parallel lines, skew lines, or perpendicular lines? So can you eliminate? They don't lie on the same plane, so they're not coplanar, are they?
Right, because coplanar means
Okay.
on
Are they parallel?
Well, they don't touch.
They don't touch, but we don't know if they're parallel to each other, do we?
Good point.
One could be going east and west, and another one could be going north and south. And because they were in parallel planes, they'll never touch. Yeah? Are they skew to each other? Maybe. Because are they perpendicular? We don't know.
We don't know.
So they'd be skew.
Yeah, I think you're right. It's kind of an unknown.
Yeah. We know they're skewed to each other. We don't, because they're in different planes, right? They do not lie in the same plane. But we don't know whether they're running parallel or perpendicular if they were to intersect. If the planes were to...
Anyway?
S-K-E-W.
Yep. Yeah. I just had to say that because I heard you had to.
All right, you heard my hesitance? Is that
Yeah, you were like, it's K-E-W, and I'm like, yep.
All right, let's see if I can find more little fill-in-the-blank statements about stuff from like chapter 1. All right, here we go. Consider these statements. Every square is a rhombus. Do you agree? Every square is a rhombus. So they start out with that statement. Every square is a rhombus.
I guess.
Yeah.
Remember the properties of
Remember the little planet or the little world of quadrilaterals? And you have a quadrilateral that then you can stem from that, and you have parallelograms and rectangles.
Yep.
And a rectangle, well, you have parallelograms. And a rectangle is a parallelogram. Then you have a rhombus. A rhombus is a parallelogram, but it's not a rectangle. And then you have a square, which technically meets the definition of a rectangle, and it meets the definition of a rhombus, and it meets the definition of a parallelogram, and it meets the definition of quadrilateral. So every square is a rhombus. Quadrilateral ABCD is not a rhombus. So you have a quadrilateral ABCD, but it's not a rhombus. So, okay, it could be a rectangle, couldn't it?
Yeah.
Could be a parallelogram. It's not a rhombus. All sides are not the same. Every square is a rhombus. Which of these conclusions can be made when you use both statements? So every square is a rhombus. Quadrilateral ABCD is not a rhombus. Which of these conclusions can be made using both statements? ABCD is not a parallelogram. Does that work for every square is a rhombus? ABC is not a parallelogram.
ABCD.
Is a square a parallelogram? It's the definition of a parallelogram.
It has two parallel sides.
Yeah. Does a square have two parallel sides? Opposite sides? Yeah. So square is a parallelogram. So is a rhombus. So that one, the ABCD is not a rhombus. We could say, well, yeah, it possibly could not be a parallelogram, but because we have to meet the conclusion of both statements, that's not going to work for us. All right. ABCD is a rectangle. Every square is a rhombus. Quadrilateral ABCD is not a rhombus.
Well, it didn't really say specifically what. Did you say quadrilateral?
Yeah, quadrilateral ABCD is not a rhombus. Every square is a rhombus. Quadrilateral ABCD is not a rhombus. So ABCD, could it be a rectangle? Meaning that every square is a rhombus, but every square could also be a rectangle.
Yeah.
Maybe. We don't know. Well, it's a little tricky there. How about ABCD is not a square? Well, if every square is a rhombus and ABC is not a rhombus, then would that mean then ABCD is not a square? Ooh, that could work. We could be doing the inverse, couldn't we? If it is not a square, it is not a rhombus.
Yes.
ABC is not a square, so therefore it's not a rhombus. What do you think? Think we found it? I think we found it.
Yep.
Yeah. Yeah, you had to kind of take your time and break that down. All right. Let's see, what else can we look at?
Wow, it's almost already 11. It's like 10.
What's that?
It's already almost 10 to 11. It's shocking.
I know, it's crazy. All right, here's a question for you. 3, 5, 7, and 11 are prime numbers. Do you agree?
Yes.
What is a prime number?
That's a number that can only be multiplied by one in itself.
Good. 4, 6, 8, 9, and 10 are composite numbers.
Those are can be multiplied by different multiples.
Good. Factors, yeah.
Yeah.
Tiana makes the conjecture that prime numbers must be odd based upon that pattern she looked at. Prime numbers must be odd. Which statement is true? A, this is an example of inductive reasoning, and the conjecture is valid. B, this is an example of inductive reasoning, and the conjecture is not valid. C, this is an example of deductive reasoning, and the conjecture is valid. D, this is an example of deductive reasoning, and the conjecture is not valid. Are there two choices you want to throw out right away?
Well, I could agree that it's inductive.
It's inductive reasoning. Okay, so you want to focus on inductive reasoning. Now you have to decide whether it's valid or not.
Right.
So she made the conjecture that prime numbers must be odd based upon that pattern that she was observing. What do you know about prime numbers? What's the very first prime number? Based upon Tabitha said it has to have a factor of only 1 and itself.
One.
Well, 1 can't be 1 and itself.
Oh.
So it only has one factor, 1. Right? Okay. What about 2?
Oh,
Oh.
what about 2?
What about 2? Is 2 a prime number?
Yes.
Yeah. What are the factors of 2?
1 and 2.
1 and 2. So is that odd or even? The number 2?
It's even.
It's even.
You have tissues.
Yes. There is one even prime number. It's the number 2. So if Tiana says that prime numbers must be odd,
That makes it sound like they have to be odd. Well,
that's not true, is it? That's not valid.
Right.
To better state it, what could she say? She could say all prime numbers except for the number 2, after the number 2, are going to be odd. They must be odd because all composite numbers, they have more than 1 in itself as factors, and if they're even, they're always going to have a 2 in it. They need that 2, don't they? So Tiana kind of messed up. But based upon the numbers she was looking at, she forgot or didn't know to put a 2 there. Looking at the numbers she was looking at, she would say they must be odd. But then you got to go, wait a minute, I need to double tap into what I know about the definition of prime numbers and composite numbers. And I know that the number 2 is a prime number and it's even. Okay? So we would have to choose inductive reasoning, but not valid. Okay?
I agree.
All right. All right.
Well, you're right. It is already almost 11.
Here's another conditional statement. If an angle measures 30 degrees, then it is acute. What is the converse of that statement?
The converse
Mm-hmm.
is if an angle is acute, then it measures 30 degrees.
Good.
Which is true, but it doesn't really have to be 30 degrees. It could be like 20 degrees.
Yeah, you're right.
It could be 10 degrees as well.
Yeah, good. So you're right. You gave a counter example for it not being true, not valid, but you wrote it correctly. You flipped it, right?
Yeah.
So if an angle is acute, then it measures 30 degrees. And the converse does not work for us, does it?
Yeah.
But you wrote it, and we're right. You just have to say it's not valid.
The original statement, I mean, that makes sense.
Mm-hmm.
Um,
Yeah, if an angle's 30, then it is acute. That's a valid one, isn't it? Mm-hmm. The converse is not. If an angle is acute, then it measures 30.
Yeah.
All right, here's another one to practice. We're going to find the inverse to this. So if a figure is a pentagon, then it has 5 sides.
So we're looking for the inverse.
So you're doing the inverse.
So for the if a pentagon what was it again? Sorry.
Inverse. If a figure is a pentagon, then it has 5 sides.
Okay, so if a figure isn't a pentagon, then it wouldn't have 5 sides.
If a figure is not a pentagon, then it would not have 5 sides. Good. That's the inverse. Just negate it, right? Without flipping it. No flippy. If you flipped it, what do we call it?
If you flip it and inverse, it would be a consequence.
Good.
And then a converse is just flipping.
Just flipping. Good. Good, good, good. All right. All right. Which statement is true? A postulate is accepted as true without proof. A theorem is accepted as true without proof. Definitions can never be used as reasons in a proof. Theorems can never be used as reasons in a proof. So there are 2 things we can throw out. The last 2. Okay, now we got to figure out a postulate is accepted as true without proof. A theorem is accepted as true without proof. Which one do you want to say is true?
I'm thinking first. Ouch.
A postulate is accepted as true without proof, or a theorem is accepted as true without proof? Which one do we accept without proof? A postulate or a theorem?
I think it's a postulate.
It's a postulate, you're right. A postulate we accept as being true because we've observed a bunch of stuff, right? And we just haven't found a counterexample yet, right? Where a theorem we get to by using our definitions and postulates and proving them, or potentially other theorems, okay? So a postulate we just accept as true. All right, how about this? 2 unique planes intersect. So we get 2 planes intersecting. You visualize that? Like maybe the wall and the floor.
Would that be?
Or your tabletop and the sides. Which geometric term describes the intersection? A line, a plane, a point, or a segment? 2 unique planes intersect at exactly what?
A point.
Hmm? Planes would only intersect at one little point. So my floor and my ceiling is only going to intersect at one point?
Oops.
Oops.
No.
You want to change your answer? Where 2 unique planes intersect at a line, a plane, a point, or a segment?
I think it's a line.
A line. All right, you're right, a line. Because planes go into infinity, so a line goes into infinity. You wouldn't want to say segment, even though in our room, where the wall intersects with the floor is a segment from wall to wall, but we want to remember that planes travel into infinity in all directions, right? But they're going to intersect at a line. Good. All right. These are good reviews. This is coming kind of from chapter 1 and chapter 2, isn't it?
It works.
Yeah. All right, here's another one to think about. Lines L, M, and N lie in the same plane. So you kind of hang out and think about L, M, and N. You got 3 lines hanging out in a plane. So let's think about our floor as a plane, and we've got 3 lines lying in same plane, the floor. Line M is perpendicular to line L. So we've got a line M running through our plane, and we've got line L being perpendicular to it. What does that mean, perpendicular?
They cross.
Cross?
They cross each other, sort of, at an angle.
What kind of angle if they're perpendicular? 90-degree angle. Okay. Line N is perpendicular to line L. Which statement is true? Line M and N are perpendicular. Line M and N are parallel. Line M and line N will intersect. Line M and line N are skew. So what you could do is maybe take some manipulatives. You could take, like, 3 pencils in front of you or something. You could ask for some manipulatives, right? And or 3 straws maybe, or some sort of thing that you could create lines with, right?
Yeah.
And if we took, like, maybe a whiteboard and that was our plane, we put a line, and then we said that's line M. We put line L perpendicular, and I just put line L perpendicular to it, right?
I see that, yep.
And then it said line N had to be perpendicular to L. Well, then it's got to cross L it's going to crossing at the same angle as M, 90 degrees. So it has the same slope, doesn't it?
Yeah.
My straws kind of fell apart there for you, but are you following me?
Yeah.
So M and N, they're at the same angle to line L. Line L has become a transversal, hasn't it, of those 2 lines, because it's intersecting them at 90 degrees. So our alternate interiors, our alternate exteriors, our correspondings, our consecutive, they're all 90 degrees.
Yeah.
So what would line M and N be to each other? Parallel, right?
Yeah.
Parallel, because line L is the one perpendicular to them, right?
My bad.
Yeah. There's no way they're ever going to intersect. Now, could you have eliminated a couple of these? Like, could you have eliminated line M and line N are skew? Because what's the definition of skew lines?
They're sort of.
They're not perpendicular.
They're not.
Skew lines are not in the same plane. They're non-coplanar, right? So you could eliminate that one. Line M and line N will intersect. Well, we got to think about that. Line M and N are parallel. Well, those counteract each other. So, line M and N are perpendicular. Well, if line N is perpendicular to L and L is perpendicular to M, I don't know how I could get that to happen.
Yeah.
I could probably eliminate that one. So now I'm on the B or C. Are they going to intersect or are they not going to intersect? So now I got to think about this. I could even hold my finger up in the air and say, well, my index finger straight up and down is line M, and I take line L and I run it perpendicular. I have to cross it with my other finger, don't I? And then I have to make a line N perpendicular to L. Well, the only way that would happen is if I had another finger going through L at a 9-degree angle. Oh, I'm going these 2 lines straight up and down. Same angle. I've got parallel lines, right? Okay. It's a little tricky. You got to figure out how you're going to think about that and maybe ask for a case to say, can I have some pencils or pens or something? I need to create some lines to look at this, right? You could create your own tactile.
That off of our test thing. I'm really glad they didn't do that.
Do what?
So we couldn't have manipulatives in the test. Because you know how you have to, I think you have to cross it off or something on some sort of IEP or whatever.
Oh, yeah.
Back in public school, they forgot to do that one year.
Oops. And then you didn't have manipulatives available to you?
Oh, I did. I had them, but I wasn't allowed to use them, and then we had